name is Dr. Esther Trufan, and in this video, we're going to explore intermolecular forces. The first thing to consider when talking about intermolecular forces is determining if the interacting molecules are polar or nonpolar. And to determine the polarity of molecules, we have two important considerations. First, do they contain polar bonds? If yes, at least one, then they have the potential to be polar. And second, the symmetry. If the polar bonds inside the molecules are arranged in an unsymmetrical arrangement, then we are going to have a polar molecule. Once we determine whether our molecule is polar or nonpolar, we're ready to establish the type of intermolecular forces that may exist in a sample that contains a large collection of these molecules. Intermolecular forces are attractive forces between molecules and not inside the molecule. So in this case, we don't care about whether we have single, double, or triple bonds. All we care about is whether our molecule is polar overall or not. London dispersion forces are the most common intermolecular forces because these exist among all molecules. For nonpolar molecule samples, these are the only intermolecular forces that exist. But for polar molecules, there will be others. Let's look at a couple examples here. If we have methane and carbon dioxide, that gives us two molecules that are both nonpolar and making the only possible interaction between them a London dispersion force. If we just have a large collection of methane, we also have London dispersion forces between the different methane molecules. Same with the carbon dioxide molecules as well. When it comes to our gasoline, this is a really good example of a mixture that is held together by London dispersion forces. Our gasoline contains organic compounds that are all carbon and hydrogen containing, making them all nonpolar, and the only force holding them together is the London dispersion force. Another type of intermolecular force is the dipole-induced dipole interaction. This force exists between polar molecules, and that connects to the dipole component. Polar molecules have a dipole moment, and nonpolar molecules are going to be connected to the induced dipole in this description. So nonpolar molecules by themselves don't have a dipole moment, but the presence or the proximity of a polar molecule can induce one temporarily for a very short amount of time. This is the main reason why there is some oxygen dissolved in water. Oxygen is a molecule that is comprised of two oxygens doubly bound that share a pure covalent interaction. So it is nonpolar. By every definition, oxygen is nonpolar. And water is by every definition a polar molecule. And yet there is a potential for a very small amount of a nonpolar molecule dissolving in a polar liquid. And we know that this happens because fish breathe underwater. So they have a way to access this very small amount of dissolved oxygen. The same thing can happen if we mix some gasoline and water. The dipole-dipole interaction exists only between polar molecules. And this is connected to the dipole moment of polar molecules. The stronger the dipole moment, the stronger the dipole-dipole interaction. So we can look at the attraction between dichloromethane and chloroform. These two liquids are miscible with each other, and because they all contain at least one polar bond in a non-symmetrical arrangement, both of these are polar, giving us the dipole-dipole interaction. We can also look at a large sample of formaldehyde. This is a polar molecule, and if we have a large collection of these, then the interactions between them will include the dipole-dipole interaction. Hydrogen bonding is another strong intermolecular force. This will exist between polar molecules, but not all polar molecules, only the ones that have a direct hydrogen-nitrogen, hydrogen-oxygen, or hydrogen-fluorine bond. And this includes a lot of biological systems, including DNA or proteins, where we have these nitrogen-hydrogen and oxygen-hydrogen bonds across chains. The most common example that you may find as a demonstration in the general chemistry laboratory is water and ammonia. And if you've seen the experiment called ammonia fountain, you see the very strong attraction between water and ammonia. And this all comes down to the strength of the hydrogen bonding interactions. There are some other considerations. For example, there may be multiple types of intermolecular forces. And the more type of intermolecular forces there are in a system, the stronger those interactions are. And that translates to higher boiling points. So systems that have strong intermolecular forces will also have a fairly high boiling point. Methane is naturally a gas because large samples of methane only have London dispersion forces between them. However, water under normal conditions is a liquid and it boils at the fairly high 100 degrees Celsius temperature, which means that the attractive forces between the water molecules are substantial. And those include London dispersion forces, which exist between all molecules, dipole-dipole interactions that exist between all polar molecules, and water is polar, and then hydrogen bonding interactions, which exist between all polar molecules that additionally have oxygen-hydrogen bonds in them.